Say good morning and
the sound and everything goes through. Do you have any? Yeah. It should work now. There should not be any. Yeah. Right. Yeah. And now
Now I can.
you can just present.
Oh, okay. Continue.
We can even cancel it. I don't need it.
I don't need this either, and I can just.
Then, yeah.
Oh, hold on. Hold on.
Yeah, slightly. And then, yes, the meeting already. Yep.
Share. Window.
Yeah, show Windows this one. Yep.
So are the numbers updated? Well, I assume it. Okay, we're done.
And this clicker works too. So
Okay, now.
It was the video world.
no, I mean, that's all that's it. So,
Yes, you can, you are last. Oh, yeah. So oh, MSF is
Papa. Hello. Okay, everyone, please take your seats in the interest of time. Please take your seats, grab your coffee, food. Take your seat.
Just what do I do with it? Do I stick it? Do I give it to somebody?
Here are the guys running the show. Hello, everyone, and welcome to this final review of our NASA University Leadership Initiative project on robust, resilient autonomy for advanced air mobility. Before we get started, we have our Associate Dean for Research, Dan Bodany here, who has a few welcoming remarks to share on behalf of University of Illinois. And then I'll go ahead, introduce the project, and get the mic for team members to present their individual contributions. Dan, it's yours. Do we have to hit the record button?
Ready? All right, good morning. All right, again, good morning. All right, you're here for 2 days to listen to Naira and team talk about advances in assuring safe and autonomous flight systems. And as Naira said, my name is Daniel Bodony. I'm a professor of aerospace engineering. And for this role, I'm wearing my Associate Dean for Research and Graduate Programs hat. And on behalf of Dean Bashir and the Granger College of Engineering, we welcome all of you to our campus. You brought good weather with you, so please stay and let that good weather continue. And special thanks to NASA and the advisory board for facilitating, advising, and guiding the center. AVIATE brought together universities, industry, and importantly, flight test capabilities to address a central challenging question facing the future of aviation: how to make autonomous air mobility safe, robust, and resilient. As a former private pilot and an active air acoustician who advises the government and industry on the intersection of acoustics and autonomy, the goals of this center speak directly to me and the challenges that are on the horizon. And I know that this next 2 days will be fantastic in reviewing their progress. The project produced a strong record of scholarly output, but fantastically demonstrated those outputs in the field with the flight test capability near in Nevada. And we're very grateful to see that progress. So my remarks are very short. On behalf of the Granger College of Engineering, thank you so much for coming to our campus. If you were visitors and taking part, if you're listening remotely, thank you so much for your participation in the center overall. I want to recognize Naira and her leadership team for leading the ULI through its paces. And we at the university and the college are proud to host this review. So I hope you have an amazing 2 days. Thank you for your attendance. And Naira, I'll turn it back over to you.
So before I get into So first, I want to thank for the flowers. It was a nice surprise. So we have even flowers to celebrate this event. And to get started, let me just move forward and introduce our outstanding team. So if I have to put it briefly, I would say that exemplary leadership, scholarly excellence, and community engagement are the words that I would use to describe my team members over this journey of the past 4 years. We have exceptional scholarly impact and output. We have industry practitioners who tirelessly worked to leverage their also internal and other sources of funding to ensure successful flight tests on major platforms. We have outreach coordinators that tirelessly worked to reach out to Urbana Middle School of Girls or places like Girls in Aviation forums and other events that maximized our impact through this process. So in short, we have professors from MIT, Georgia Tech, North Carolina A&T University, University of Nevada at Reno, University of Illinois as expected, and Lockheed Martin and Sierra Nevada Corporation were our transition partners. And before I go ahead, I just couldn't miss this major milestone that we all were very excited and very proud to feel that we work with a team from Lockheed that built the Orion capsule, with NASA that enabled the mission. And the keywords that we've captured here is what was being emphasized throughout the 10 years, the unforgiveness of space engineering. Equally unforgiving is the commercial aviation and today's advanced air mobility industry that deals with human lives. I decided to do a brief historical overview. When I came to this country 28 years ago, the aerospace industry was presented through these big vehicles for me at Georgia Tech. I was coming with a PhD in math and had to work on stability of these flight control systems. Everything was big, huge, humongous. And as I worked 28 years in this country, everything got kind of miniaturized, small scale, autonomous, human-centric. And these developments were enabled by the data explosion that came with the hardware development of making CPUs and GPUs cheap and available. LLMs and VLAs became a common marketplace. Consumer markets like parcel delivery, emergency response, agriculture became also part of the problems for aerospace industry. And yes, the commercial aviation over the 100 years, by enforcing zero tolerance to accidents, has achieved safety and public trust by flying 4.5 billion passengers per year. The same cannot be yet claimed for the low altitude, where the advanced air mobility developments are happening. Just last year near DC airport, a passenger airplane crashed into a military helicopter, or better to say the military helicopter crashed into a passenger airplane, causing catastrophic kind of failure and death of so many passengers. So the low altitude space remains largely vulnerable to different uncertainties, unpredictable circumstances. And the problems that appear here have to do a lot with autonomy, with optimization, with deconfliction, path planning, mission management, and many others. Let's look, what do we mean here? So in low altitude space, we are thinking about emergency response, about healthcare, about the travel time to be optimized, cargo delivery, and many others. So the technology that can tackle it, what we are trying to solve, should deal with the scale, the complexity, and also the safety. So for that, we need autonomy with assured safety. The technical challenges that were formulated through this ULI program are 4. The first one is safe learning-based perception and control, where we're trying to integrate different learning-enabled components into L1 adaptive control architecture or other architectures that were kind of expanded here through collaborations like simplex architecture that we have developed with Luisha for integration of gain learning enabled components. We have fast data-driven and code level verification that Mitra is leading. We have runtime fault diagnosis and reachability analysis that's being led by our North Carolina A&T University. That's an R2 university. We had a major technical challenge trusted to them. And we're testing evaluation and integration towards technology transfer, under which we developed all the flight tests that we had. This University Leadership Initiative culminated in a major Autonomy Fest flight demonstration at University of Nevada, Reno last year, led by Christos Papachristos, who worked closely with Evangelos Theodorou from Georgia Tech and Sierra Nevada Corporation. Within 2 days, they demonstrated takeoff and landing on the water, vision-based landing of small UAVs. They did covariant steering, like obstacle avoidance up in the air, where you see here the kind of machine learning enabled path planning coming from Georgia Tech, flying on the vehicles of University of Nevada at Reno. And Christos will give a big overview of this. Another major culmination of this University Leadership Initiative was the flight test of Lockheed Martin on the Vista platform, at the heart of which is the L1 adaptive controller. This is a historical chart of the L1 adaptive controller that we started to develop in 2004-05. The objective of it was to solve the transient performance issues of the conventional adaptive controllers that were sensitive to delays and disturbances and could result in loss of robustness. With the decoupling of control and estimation loop, L1 adaptive controller solved the transient problem. And through NASA program with the flight test of subscale commercial jet, Boeing 757, 5.5%, we commercialized it across a number of industries. We were able to test flight on Learjet and F-16 at Edwards Air Force Base. Jessica is here. She was our flight test engineer. And finally, Lockheed Martin put it on Vista, claiming TRL-6. Here is a brief snapshot, and they will go deep into it through their presentation. TRL-6 at 3G maneuver with hit to gas, failed right flap. Here you see the time history of the signals. And the paper that was published by Lockheed Martin in last year American Control Conference is cited here. The paper summarizes the flight test overview and shows the architecture that was flown. With that, I would like to give an overview of today's presentations. We will move from TC1 that has safe learning-based perception and control. Luisa will present the perception simplex, where we have extensions already to accommodate perception uncertainties in the simplex architecture. They will give a good overview. We will give an overview of this ontological robustness, what we call, that's a language of communication between machine learning enabled components and also L1 adaptive controller. Why do I emphasize it like language of communication? Because these vision-based sensors operate with learning enabled components that have stochastic modeling. L1 adaptive controller was developed in deterministic setting with conventional gain and time delay margins. So we made sure that the two can talk to each other rigorously, instead of saying we tested everything in simulations and works. And I will have one of my postdocs, Aditya Gahlavat, who is not here yet, but he will soon come, to present these developments, because he did most of the mathematical developments. We'll have TC2, certifying Urbana air mobility scenarios. Sayan Mitra will present, and Chuchu is away, but I heard that her postdoc will be here. We will move to TC3 for runtime fault diagnosis and reachability analysis. For in-flight contingency management, we have all the co-PIs here who will take over and do this presentation. And we'll have Christos summarize the flight tests from last year's Autonomy Fest, because that was real-time physical flight testing. So the data has been collected, analyzed over the past year, and we can now show nice results. Vasu Salapaka will talk about network logistics and planning problems in airspace management. As we know, NASA is very keen about the outreach program, the scholarly impact, the number of students who have graduated, the course development. Sayan has developed this wonderful course, EC 484 here, Principles of Safe Autonomy, where he uses some of these algorithms that he has developed, the verse toolbox. Within the course, the students are publishing papers. We are famous scholars, no doubt. We get invited for keynotes, we do different presentations, we get different awards. And here we have summarized some of the new grants that were developed based on the basis of this work and some of the awards that our faculty members were able to get through this program. With that, I would like to invite our first speaker. James, ready? So I think the most important is the major industry technology transition. That's why James gets the first slot. Oh.
We lost the audio.
Sorry about that. Does this work now?
Yes, thank you.
Hey, Kevin. So,
Morning, James.
so I'm just going to give a brief closeout summary of the work that we were able to do, testing out some of the L1 controls. So first, I want to thank Naira for selecting Lockheed Martin to be a participant in this very important program. I think personally there is a great opportunity for industry and the academic world to come together to do some great things, and this is just one example of it here. And when you're first, you get to work out all the kinks. But
How about this? Try
let's
this.
see.
Oh, I see. They should work now. This works. Yep. Okay. Should work.
So, yeah. Okay, so before I get into just the a summary of the flight test, I did want to at least do sort of an executive summary of how I kind of view the program and the intent and kind of what we were able to achieve kind of working together here. And as I mentioned, just a moment ago, I think it's important for us to leverage, ideas, technologies from different facets of the technical community. So from the academic setting into industry, I think being able to take theoretical findings and incorporate those into actual software that flies on platforms is a great feat. And it takes a lot of work and a lot of communication an effort between people. And so this is, I think, one example of that can serve almost as a template for these types of activities. So again, the idea is to identify technologies that we can actually fly, and so that is sort of point number 2, which is the basis of this talk. And then from there, when we go fly something, well, what did we learn? What are the lessons? What can we improve? Even looking ahead, what should we, take into consideration now in order to be prepared for the future? So those types of ideas and concepts are important. And making recommendations is one component of that. And then when we started, we kind of talked about FAA certification. I would probably extend that beyond that and also consider military certification, which is a little more, it's less stringent than the FAA certification process, but it will give us opportunities to actually mature more technology and get it out into aircraft, vet it, and then see where we can actually place it on platforms. So back to the flight test. So the idea, so this was started way before I even, became involved in.
That's fine with me if you want to do that. It's fine if you want to do that.
Okay. Yeah, I was like, fine. Maybe. I actually do want to fly something else on here, so I was like, okay, maybe getting ahead. Okay. But so the Vista aircraft allows us the opportunity to actually take technologies, put them in this test environment with safeguards, so that we can really push the envelope with the technology itself without, a concern of, risking, the safety of the pilot in this case, or the aircraft itself. And so L1, Chris Elliott, who was formerly with Lockheed Martin, had a lot of communications with NIRA. And so when I came on board, he left. And so it was my job to actually finish the work that he started there. And so to that end, we looked at the safe block that's shown there is sort of our experimental block for controls. And so we can put whatever we want in there as long as we can get clearance to fly it. And so in this case, L1 is sitting inside of the safe block there. And it provides inner loop augmentation for the flight control system. If we're talking about a pilot, then it ends right there as shown, but you can imagine that if you do this on a UAV, of course, then you'll have outer loops and you'll move on out to guidance and et cetera. But the idea is to ensure that we're stable so that you can do all of the other tests that you want to do. So if you want to put AI on here, you want to do more complicated tasks, you really want to have a good, strong inner loop controller. And that's the idea. So I won't go through the block diagram stuff. It's only 15 minutes. Love to talk through it. Okay, but here's like a key takeaway, this, which highlights the robustness of the L1 control. So we wanted to kind of do several tests. As you can see there, I have 4 tests listed. A CG bias, a right flat lock at 0 degrees, reduced rudder effectiveness test, and a left elevator lock at 0 degrees. The last test there, as you can see, it was scrapped. And the reason it was scrapped was because the actual vehicle will not allow you to have more than, a few degrees of differential elevator. And so as a result, if we locked one and we needed the L1 to actually sort of fix something, it would have been overly constrained there. And their issue was that if you get too much twist on the tail, it could actually break. So we're like, okay, fine, let's scrap that one. That was the one that we actually tested in our dome sim, the left elevator lock. We brought in pilots to actually fly it. And so that one went well. And so we were confident that that would have been a good test. So we get there and they're like, no, you can't do that one. And we're like, okay, well, let's do the roll axis test. Okay, so we'll lock the flap instead. So that one, again, just put L1 to the test because it wasn't one that we actually really tried to tune the controller for. We're like, okay, let's go to test aircraft. Again, we did CG bias, and then there was reduced rudder effectiveness, where we just basically put a multiplier in the code on the rudder control effort. We could do 75% effectiveness, 50%. The test pilot school actually wanted to do 0%. They just said lock it. And I said, it's not a good idea because that's all you have for your directional control. And they said, well, we're going to do it anyway. And I'm like, okay, sign here. And then you can go and do this. And they did it. And they said, oh, we can't control the aircraft. And so we're like, yeah, okay. So then they kicked out of it. And, you know, everyone was happy. So they were able to do what they wanted to do. And I was free of any culpability or. Now the one that I will show you that Naira kind of had up before was the one where we locked the right flap and we said, okay, execute this heat to guns maneuver where the, if you remember one slide back, the two aircraft there, the one in the forefront is Vista and the one in the back is the T-38. And so they're able to go up and then fly maneuvers. Okay, and so the heat to guns was actually a maneuver where Vista was trying to acquire and track the T-38 in a 3G turn. It was something that typically they would do, and it kind of the video shows like, okay, if you're compromised in terms of your roll effectiveness, you're going to have a difficult time doing that without some augmentation or some aid. And so L1 allowed them to actually acquire that much better. And so that was sort of the test that got us more money to continue doing more safe controls within Lockheed Martin. The other piece that I want to point to here is this flight envelope, which doesn't have the scales on it. The red dot is where we actually tuned the L1 in terms of the filters. We set everything up there. But for this test, we allowed the pilots to fly wherever they wanted to fly. So again, when we talk about robustness and we're talking about sort of saving time doing controls, if I can just go and tune at one place and then go fly at many other places, then that is a benefit and a testament to the robustness of the aircraft, right? I don't have to necessarily go through and do an intricate schedule, which is, typically, what happens. You go to, different flight conditions, design your control laws, your gains, and so forth. The box that's shown there is where the maneuver, the heat to guns maneuver and the video actually occurs. So you can see that where sort of the separation between where we tuned and where actually, the flight test in terms of heat to gun was actually performed. So it's quite a ways away in terms of flight conditions. So here's some data from it. This is the pitch axis. This was not a pitch axis failure, and so as you would expect, the tracking with the L1 off, safe off compared to safe on, they're about the same. So, but when you go to the roll axis, and as he's trying to execute this heat to guns in the bank of turn, the flap being locked introduces a sort of bias in the system that was not corrected. So we didn't do anything with the mixer to say, okay, if there's a failure, okay, take actions A, B, C, D. We just wanted to test this strictly on the simplest mixer possible, just to determine how much, the augmentation would help us out here. And so going from safe off to safe on, you can see that certainly you would expect if we were to convert this into a video, which we do in the next slide, right, the tracking is going to be much better on the right side. And so now back to this video, which you saw already, but when the Air Force sent it to us, just put it on loop on my laptop. I just let it play like all day. Every time I look up. But and so here on the right side here, safe off, you can see that he's having difficulty trying to lock into the center piece there. And this one I didn't put in the loop, but on the left side, you can see that he's far more steady and he's really trying to track the blue square that's inside of here. Okay, so he's actually able to lock onto the T-38, which is in the background. So in closing, we were happy to be able to participate in this program. And also grateful that we got some results that we could actually show and demonstrate, the capabilities of this technology. So the idea is to continue forward. One thing that's of interest to me personally is the reachability analysis that we've been working on here. That would be of interest to kind of get that into a system to determine that if I'm at location A, I need to get to location B. Then given other constraints like fuel, winds, et cetera, exactly how close can I get to B? What other points can I get to if B is no longer an option? So now when we do reachability analysis, it kind of tells us, okay, you can get to this point with this much fuel, et cetera, et cetera. And that's going to be important for autonomous vehicles where you're flying. You have a plan, as we all do, but we know that plans change in real time. And so how do we get technologies in that would advise an AI agent on, what decisions it should be making, what constraints to take into account, what physics do we need to be cognizant of as we're flying these vehicles. Okay. So I'll end right there, and I want to thank you for your time. And it's great to see you all.
Thank you very much for a very interesting presentation. And it looks like L1 is not just getting rid of the smoothing the transients, but it's actually getting rid of all of them from what you showed. And this is consistent with what you showed, the red dots where the L1 was tuned with respect to the distance from the parallel ground that the test flight was happening.
Mm-hmm.
And would you say that essentially L1 is able to pinpoint the sweet spot where robustness maximizes? And it's sort of like a structured and advanced AI learning system, but in a very smooth way.
Mm-hmm. I guess I would categorize it more in the sort of domain of robustness versus, something where it's, modifying things on the fly necessarily. So when we set those filters, I think that filtering component, I think, is important because it sets the bandwidth and it says, okay, I'm going to reject basically, or I'm going to attenuate anything above, right, a certain level. So that means that, when I have disturbances that are outside of that bandwidth, well, I'm going to be robust to those in a certain way, as long as, right, the remainder, the remaining part of the system in terms of the gains and how we're setting, the effective proportional integral gain part of it, how well that's tuned. And that combination, to me, gives us kind of this extended domain of attraction that allows us to sort of go out beyond what a normal linearized based controller would do.
Yes, the system for L1 to really work out this miracle once it is tuned. This is very satisfying.
Mm-hmm. Absolutely.
Thank you very much.
Mm-hmm. Yeah, thank you.
Okay.
Thought I was getting away. Just
Can show that
I moved too slow.
So I think, I'm not biased when I say the human, well-trained aviator that knows their aircraft is the best learning adaptive control system there is, right? So L1 is an inner loop and it does really well with what you tell it to do. So and you kind of talked on it, on the reachability analysis, but I think the challenge is to now take this one step beyond, right? So you can pick like Sioux City, Iowa, or Sully on the Hudson, or, you know, two hornets that collide, and one of them has missing a third of the wing or a quarter of the wing, and it comes back just fine. And so how do you take this inner loop and now wrap it with the intelligence that you were describing, right? That's the next generation of this is how do I, okay, some fault has occurred. How do I quickly learn enough and make intelligent decisions like, hey, I really can't go any slower than this, right? Or left turns are out, you know, all I can do are right turns from here on out, whatever the case may be. So, and I know you touched on it, but you know, that's really where this has to go. When that happens, like that outer learning element, then, you know, hands down, this is the best stuff around. Hey, just more of a comment, but I like where you were going with the reachability analysis and that, because that's really, for fault tolerance, that's really what's required next.
Absolutely, yeah. Yeah, I'll respond a little bit to that, since it's not a question, but it does kind of bring to mind some ideas. When we talk about, when I think of what's happening with AI right now, and I think there is room and a space for AI L1 or AI dash, whatever your favorite like methodology is. But those have to, so there's the physics side of that, and I'll bring that up because I'm a physicist, actually, first. But when we talk about, you know, either combining, you know, the physical elements or either aerodynamics, mass properties, whatever, you know, those may be, and we combine that with something that's looking at errors and it's kind of making decisions moving forward, there has to be a certain consistency there. And I think that's where, when we talk about putting something like L1 or making L1 behave like an outer loop, I think it will need to happen in concert with technologies that are actually gathering that information, right? So someone has to, you know, in order for me to make a decision here, someone has to tell me at least what the talk is supposed to be about, right? So this sort of information gathering, I think, is important. How do we do that fast? Okay, and how do we do that in a robust way? Robust enough so that the L1 type technologies can compensate for, you know, components in the information vector, as I'll call it, that may be missing or that may be uncertain. So it is going to be a challenge, but I think it's a fun problem. And there's lots of methods that are out there that I think we should never discount or say, that doesn't apply. We really need to look at a lot of different methods. So, but I can stand up here and talk all day about stuff, and I know we want to stay on schedule.
Hey, do you mind if I make a make a comment? I really don't like the use of the word learning in this controls. I mean, this isn't a learning algorithm. This is an adaptive control dominating a disturbance. So learning is more of an indirect adaptive versus direct adaptive. This is a direct adaptive control law. Disagree with that, James?
No, I agree. Yeah,
Okay.
certainly. And I think that's why we need these other components. So one sort of indirect methodology, when we talk about parameter identification, that's an area where you actually learn something, you learn some physics, and hopefully real time. You then use that information to inform something like L1 or something that's adapted to say, hey, you know, the landscape or the dynamics of the system have changed in a certain way. How can I use that information to make my actual control law have to work less? Because I can put it in position so that it is not, it doesn't have to be as robust, because now I'm sort of sliding my dynamics to match the physics. Whereas if I know nothing, I just have to be robust to everything. And so definitely that's a valid point, Kevin, in my opinion.
Thank you.
So, Kevin, let me go.
Okay, I think it's on. So if I may add, so even without going into the mission level type of work, right? I would argue that where my personal perspective, where L1 buys you time, it's not just in learning my dynamics. It's giving me time to keep my aircraft flying while other algorithms not only gather information, but making decisions at a high level, right? If L1 can deal with the fact that my dynamics completely changed, I'm still controllable, which means I can still fly, because one aspect that it has is it has a nice graceful degradation, right? When we violate assumptions, I may not recover my performance, but I'm still going to be stable. And that buys me time to not only gather information about what just happened in my dynamics and reachability analysis, but it buys me time to now start making smarter decisions about how I control my aircraft. This is going back to what Mike said. I cannot turn left, or I should not be making my, roll higher than X, Y, and Z. All of that comes from learning, and Kevin, you're absolutely right. L1 is not learning, but it buys me time to do learning control while still being safe. So that's just more of a comment and the way we kind of thought about it in our applications.
Right, and I think that's spot on. When we talk about, and again, even if I go back to parameter identification, I need time to actually learn that, right? And I need time to process it and to determine what action I should take. And so when we talk about L1 in the inner loop, that's where, its greatest benefit at this point is going to come, because it controls the stability of the aircraft and it allows you time to then do things like AI, PID, reachability analysis, vision, and all of these components that we're going to hear about today. Those are elements that become possible because we have a stable aircraft and I don't have to rush and make the wrong decision because I'm running out of time. So I think that's definitely, in line with, what I think we should be doing and what we have been doing and what we're planning to do in the future. Thank you again.
Hey, James, can you hear me?
Just a quick, I think, James, do you want to take another question or you want to take maybe, I think it's online. Yes, please take, yes, go ahead. I think we can hear you. Yeah.
Oh, great. This is Eugene, if you remember me.
Hey, Eugene. Yeah, I remember.
Have you guys tried to assess like stability margins numerically, of course, since the whole thing is nonlinear anyways? Like how much time delay, excuse me, how much time delay the system input does your system, can it tolerate?
So typically, let's say we were sampling at 100 hertz. I would require a minimum of at least 3 time delays minimum. Normally, when I'm designing, I want 10. And because of the nature of this control law, you can do that type of analysis, somewhat. And, for nonlinear systems, it's relatively simple to do that component because you can just insert delays on, paths and ideally put it on every path to determine how much margin you have. So a minimum of 3 samples is what I kind of think about, but I push for far more than that.
Interesting. Yeah, thanks a lot.
Yep.
The requirement actually is 150 milliseconds for a fighter. And you can go with 80, which would be borderline. I mean, 3 delta T, that's like 30. That's not good. That's like really low phase margin.
Yeah, that's why I push. When we talk about, we're actually, and that like minimum is all the way sort of in the outer loops to the inner loop requirements are certainly, more stringent. But, again, if we were to actually, try to, put something in production and push it, I typically, just on my baseline controllers, have, 150 plus.
Yeah. I mean, that's what it take, if you were to go real on this.
Yeah.
120, I mean, 150 is the desirable number, but it has to be above 100 or it's just not gonna work.
I would have asked you, have you done any real-time stability margins with L1 active?
For this program, we did not do that. But if we go up and fly again, we'll have more time to do, more analysis, things that people might be interested in. For us, in this sort of first pass, it was important for us to just assess like failures that might occur, because those are, when we design mixers, right? A mixer could handle this, right, without, potentially L1 at that particular, point where we did it, right? But we'd have to give it all of that information. So this test was more designed to just go up, let's see how robust we are across a flight envelope that we have not prepared for, because we had that liberty to do so for this.
Very good, thank you.
Yeah, it's good, James. And not to derail anything, you guys did a good work. I was just gonna make a generic comment. Look, as you may know, all model-based controls, and this is one of them, and that's what we do, model-based control. The only reason they work is because of Bodie and Nyquist. That's really is, not Lyapunov, not adaptive, not L anything. It's Bodie. If you have margins, it's gonna work. If you don't, it won't. Predictably, I mean, it may work for a test or a 2 or a 3, and then it'll crash. So it's super important for you guys when you test your technologies, don't just focus on performance. Don't forget about robustness. It's a trade. S plus T is always identity. You can't get them both. It doesn't matter if you do nonlinear, dynamic inversion, AI, or whatever. You have to have gain and time delay margin at the system input. You have to show it numerically, theoretically, both, whatever. Just a comment.
Oh, yeah, no doubt.
So, Lockheed had a sister contract on the Restore program at Wright-Patterson alongside mine but we flew on the X-36. Naira maybe remembers, Georgia Tech was my subcontractor. That's when she joined Tony Calise's program down there. We tested not today the OBLTR approach or the L1 approach. It was more conventional MRAC, but we were able to do real-time stability margins on that aircraft under failures and show that the frequency response matched that of the model. That was really significant in proving out some of the concerns over structured mode interactions, but it also allows you to create a stability margin for certification. Okay, over. I'll stop talking.
Right, yep. And so we did real-time margins on our first L1 flight test where we flew on a Stryker aircraft. And I don't have those slides, but we showed our phase margin and we showed that L1 actually, basically there was a graceful degradation there shown. So yeah, we have done a lot of work in the frequency domain, and we do that certainly on our baseline platforms. And, I have the scripts and I do all of that kind of analysis because it's important. Here, you just don't see it here, but we do it. A lot of it. In fact, they call me Dr. Gaines. That's my nickname. Lockheed Martin. Yeah.
Okay, speaking of gains, James, you by any chance have a plot of those parameters that L1s do in real time? I mean, if you don't, you don't. It's all right.
Yeah, no, I don't. Yeah, this is just kind of what I showed before, cut down for a 15-minute talk that is now turned into a longer talk. And I'm happy to continue talking, but no, I don't have it.
Okay, thanks.
Yep. All right, take care, guys. I'll talk to you, Jim, Kevin.
Okay, that's I think we're going to move ahead with the next talk.
Hey, we lost the audio again.
All right, now that we have the technical difficulties figured, let's start. It's all that we have to share it too, right? If you go here, we have to share screen and then you have to go. Allow, share, select, open, and then yeah. Yep. Okay. Okay. I think it's already in there. I should. When I get stop sharing. And then this should work now. No, it should work now.
Are we good?
All right. Yes, I think we should. Right. We should be good. And let's just take it.
All right. Thank you, everyone. Many apologies for the delay. First of all, I'd like to say that I'm here presenting on behalf of the combined work that we did with Dr. Petros Bulgaris, who's head of the mechanical engineering department and also head of the program, the aerospace program at UNR. So this is combined work that we did on systems integration and field deployment verification. So What was our goal when we set out to accomplish the goals of this project? It was to provide platforms that already possessed a high degree of autonomy and reliability in order to be essentially the test beds where we could deploy all those learning-enabled components that were going to be developed for this project, and they would be able to be systematically tested across the UAS test sites, flight test sites that we have available near the University of Nevada, Reno. So in that, we thought to have a structured process of how we can develop essentially systems that would provide diverse flight envelopes, so through diverse embodiments. They would be able to provide diverse payload capabilities through different scales. Payloads would essentially pertain to different sensory configurations, multimodal sensors, different configurations of those, and also computational capabilities embedded on those platforms, but also provide an underlying cross-architectural framework where we could essentially leverage middleware in order to make all those systems deployable across different architectures that we would be supporting. And for the deployability of the learning-enabled components, we also needed to approach things in a way that would allow us to physically deploy those onboard even smaller aircraft for real-time verification of the capabilities that we were developing across this ULI. So one example of how we went about deployability of those learning-enabled components is visualized here, where we considered essentially also the additional aspect of how can we ensure that we have systematic repeat back-to-back testing of emergency response situations and how they are handled on board a small aircraft of this scale. What you see here is the Gannet VTOL, which is essentially a system that's capable of, it's a new generation of system, we call it that. It's perpetually deployable in the sense that it's a system that can self-sustain out in the wild. It can go out, figure out where to land on its own in environments without any kind of supporting infrastructure, and then self-sustain through solar harvesting, self-hibernation, battery-powered power state management over prolonged periods of time until it becomes necessary for it to respond to a local event that it can sense on its own proprietary sensing, and then take off and take on a mission that is required in order to perhaps take care of a local emergency situation. This one has the added capability of being able to land on water, and then it can also perform back-to-back repeat landings and surface takeoffs from water, but also be able to remain immersed for prolonged periods of time. So how did we leverage such a platform? We embedded the necessary perception capabilities and also the necessary compute capabilities in order to have a small, lightweight, deployable network where it's capable of performing pixel level segmentation of onboard the aircraft, and be able to detect certain unstructured regions of the environment that may serve as safe landing locations. And more particularly, what you see here is a case where this is deployed and around a lake type of environment in the northern Nevada region close to UNR, and it's making detections of the lake bed, and eventually takes on an emergency decision to land. So this is in line with the approach of low altitude flight that is expected for urban air mobility platforms, where whenever they are in a situation where they are flying over natural, unstructured environments, they may encounter some kind of emergency event, and they have to respond real time by taking an onboard decision given the mission parameters and knowledge, for example, of how far away an airstrip might be versus an opportunistic landing situation on board the local environment and its terrain landmarks. Now, the cross-architectural approach that we followed allowed us to also deploy this kind of algorithms and these kinds of approaches on larger aircraft and transition essentially this kind of technology to our industry partner, Sierra Nevada Corporation, who had recently acquired Volansi, which is a company that develops mid-scale hybrid envelope aircraft. And this allowed us to also leverage the increased payload that was offered by such a platform, where we could deploy now more powerful Ampere GPU frameworks, and with payloads that involved multiple cameras operating on board the aircraft at all times. Now, for the purpose of this kind of integration, of course, it's not just to give some capabilities and to the industry, but it also feeds back to us with data and realistic world situations with other aircraft as well, where we can collect essentially an understanding of how these behave across different scenarios. And the scenario at hand, which was field tested and demonstrated during the ULI Autonomy Fest, had to do with detection of terrain landmarks, which essentially would serve again as safe landing locations without necessarily restricting ourselves to the computational capabilities of smaller neural processing units, which require techniques like quantization of network weights, etc., in order to be deployable. In such a system, we didn't have to lose accuracy, and we were able to deploy much powerful deep learned strategies in order to do that. The whole approach, of course, is based on the notion of having a pilot level, human level understanding of how terrain landmarks may serve as safe landing locations, because even if you have multiple sensors on board, like you have stereo sensors that allow you to perceive depth, if you're operating very, very far away from environment landmarks, then you don't know the micro scale features. And in order to be able to detect the appropriate location which you should land on, it makes the most sense to use human level cognition, which is what a pilot would do, just based on visual appearance, be able to tell that this particular landmark is like a grass field or it's parking lot, and understand based on that whether it serves the purpose of emergency landing. Then finally, as far as the field tests that we conducted during the ULI Autonomy Fest, this is the supporting platform of the last test that I'm going to be mentioning, but I will take a second to mention what's available here. So this is the Minico platform. This is the very first perpetually deployed system that we developed that also has the self-sustained capabilities and the solar so the solar power harvesting and self-hibernation that I mentioned before, but it also has some onboard computational capabilities and sensing that allow it to perform autonomous missions. Now, what's the most interesting about this platform is that it can be very easily replicated. It's fully 3D printed design. It's very fast to build, repair, etc. And it's also been shared with partners of this ULI project, not just in terms of the designs of it, but also it's been replicated and adopted by some labs here at UIUC. So they have their own Minico platform here. So such a small scale platform is very good for repeat testing, for example, of the covariance steering algorithm, which was provided by our partner at Georgia Tech and Vangelos Theodoros group, which is an algorithm that allows systematic avoidance of obstacles with guarantees. With covariance steering, we were able to test the avoidance of several virtual obstacles which were discovered during an execution of a trajectory over the open air spaces that we have available at the UAS test site at Nevada near the University of Nevada, Reno. So this whole set of capabilities culminated essentially in a combined testing of everything across the ULI Autonomy Fest event, where we had students get the opportunity to not just present, to not just give PowerPoint presentations of their work, but present their actual hands-on work in real life, its applicability in emergency response, in emergency handling scenarios like that. But it also happened in front of a real live audience, including academic partners, including research lab leads, including also industry partners, for example, Lockheed Martin, Google Wing, our Sierra Nevada Corporation, etc. So it was a combined event where students and industry, academic, and research leads came together and were given the opportunity to witness the products of this work and how it plays out in real life scenarios. What you see here is the first sequence of this test that pertains to what I mentioned before, utilizing this autonomous amphibious aircraft, take decisions on where to land based on just detecting the fact that there is a lake in the local environment and be able to tell that this is an appropriate landing location to minimize any kind of catastrophic risks. Kind of in line with the virtual Captain Sally, which was the part, interestingly, part of our proposal when this ULI was proposed. It fit very well within the notion of this concept. Now, the second sequence of tests pertains to the covariant steering algorithm and its deployment on limited computational capabilities, but still capable of performing the execution of learning-enabled components on board, which in this particular case, the Minihawk platform. What you see here is the students leading the test. It was a combined team of undergraduates all the way to PhD level, with undergraduates, graduates, and PhD level students that led all these tests in front of the audiences. This test of course, doesn't involve real obstacles and their detection in real time, but it involves the execution of a pre-planned final descent maneuver and the virtual discovery of obstacles, which means that there has to be an adaptation of the trajectory on board, and this in order to guarantee safe landing, the covariant steering gives those guarantees such that the landing happens with guaranteed avoidance of the virtual obstacles that are being virtually discovered again during the approach maneuver. Yes, this is also, it should be indicative of the scale and of this particular aircraft, that despite all the computational capabilities and all the field potential that it has, it's very easy to repeat platform in terms of its physical physical implementation. The last thing to mention, this is more recent work. This is not something that we demonstrated in the ULI Autonomy Fest, but this is also indicative of further work that we've been doing with very different looking field testing environments. This is essentially a new aircraft that we've built that is we call the Albatross. It's capable of performing more dynamic motions. It's still capable of all the other capabilities that I mentioned before with amphibious capabilities plus onboard perception and autonomy. But here what we are developing is essentially, and what we're doing is some early testing of dynamic soaring, like maneuvering, so more agile maneuvering, tested over a desert dry lake bed, which serves as an environment where we can initially go to test this kind of more dynamic motions before we deploy them on board and close to surface skimming maneuvers that are required in order to replicate the same type of dynamic soaring behavior that you see with albatross birds, for example. This is just an indication of even further, not just testing, but also UAS field demonstration environments that we have available at the region of UNR. That's it from my side. Thank you for the attention, and I'd love to take any questions. Everybody ready for a coffee break?
So Chris, the nice thing is, when I was out there, was it less than a year ago, right? We discussed improving capabilities, onboard capabilities for some of the platforms. And it looks like you guys have taken that to heart, and you certainly are doing that. Can you chat a little bit more about this? Because you talked about the bigger UAV, that's Sierra Nevada / whatever, right? But some of the smaller stuff that you guys have in your lab, can you expand a little bit on the capabilities, better maybe computational capabilities that you now have, or what your plans are?
Yes. So for the smaller platforms, we are now considering the integration of Jetson, NVIDIA platforms on board instead of neural processing units. We have seen that they offer significant, as far as learning goes, significant increase in the capabilities of what we can demonstrate and deploy. This is also in line with the Albatross platform, which can support bigger payloads. And we believe it's going to be required in order to be able to handle situations where you need more bandwidth in detection in order to be able to respond faster, especially with those agile maneuvers that we are demonstrating and we want to be able to accomplish with dynamic soaring, close to more dynamic environments, like, for example, flying very close to waves, to surfaces of not just lakes, but we plan to bring it over to an oceanic environment and fly closer to waves. And this has, of course, bearings and relevance to be able to do more dynamic motions in environments with other types of dynamics, like, for example, in urban environments.
Yeah, just to summarize a little bit, what capabilities you guys are developing, at the end of the day, the same kind of stack has to be demonstrated before it becomes something that people adapt in industry, right? So your capabilities you're developing is precisely that. You're trying to get to where you can actually demonstrate an entire autonomy stack in those environments. So thank you.
Yes, our approach is that we don't stop until we get a field test out of everything that we've developed in simulation or any other kind of approach that we send out for research papers. We don't stop until we have a field test out of it that replicates the whole behavior in real life situation scenario and in a repeatable fashion.
This is Nina from NASA. I wanted to ask you, are you going to plan any field tests with real obstacles versus a virtual, to see how your aircraft UAVs react?
Yes, but this, of course, is reliant on having a little bit more time, especially under this ULI project umbrella. But yes, it is something that we want we want to demonstrate in a real life scenario. We've thought of several ways that we can approach, because the whole thing needs to be repeatable. We don't want to crash all the time or anything like that, as we are developing scenarios where, have vehicles flying within the airspace of an already deployed aircraft. So we have several approaches of how to go about that. But again, this is pertinent on having more time under this ULI umbrella in order to be able to demonstrate that with real life flying options. Probably not UAVs, like blimps, something equivalent to that initially, but yeah, we do plan to do that.
Apparently for the question table. Hey, great work. I just will offer, NASA is very interested in the perception and collision avoidance. T-Cubed is working to put out, so we've recently put out the baseball avoidance multi-rotor challenge and the software, and your stuff seems, very, very close to that. I just want to make you aware that T-Cubed is trying to formulate and put out a challenge in the university community. We have some schools, undergrad research projects and things that are doing it, but, I would maybe suggest that some of this gets on a quad rotor and you start shooting wiffle balls at them and to demonstrate that capability. We're in the planning stages of coming out with some opportunities to demonstrate that. So, if you want your lab to be famous at a MLB game, there you go.
Thank you for making us aware.
Stay tuned to talk at the end.
All right, if not, then let's just we have a small coffee break now, so if you want to stand up, stretch your legs a little bit, we'll start in
10 minutes.
Okay, I kept it within the 15-minute slot. That's fine. I kept it within the 15-minute slot, but didn't I? Well, not with the questions. Not with the questions, yeah.
do this and then anytime.
For the future more, just a suggestion, everybody wants to do the AVIATE on this. We just join the Zoom call, disable the audio so that you're not messing up the audio. And then in that way, you don't have to connect and disconnect. So.
Oh, so you mean?
I can join, disable the audio, use the audio that you have.
Yes, perfect.
Just do that. So in that way, you don't have to connect and disconnect. So.
Yes.
You know what I'm saying?
Yeah. I see.
Very good doing it. If you are using, are you gonna be using this computer?
Yes.
Okay. So for my presentation, just bring my laptop there.
Perfect. Okay. Perfect. Okay. I give a solution, but it doesn't work.
Yeah, no, it's fine. You always have to just say and.
It worked, right? I have to go and check there, but it looks like it's up there, so it's perfectly fine.
Why is it over here? Okay, I can minimize this.
You can. Or you can do this and this should. This is all I could do. I guess.
Okay, so move it down then. How does, okay, this is good.
Okay.
Great, here, look.
Now it should work. Yeah.
Okay.
So it was just like a Windows.
I have a habit of looking at the slides. I'll have to just.
Okay.
Are you sure?
Or 10:30 is when it was, right?
Let people come in on.
Hi, everyone. We are going to get started again.
Setting a timer.
Okay, thank you everyone for your attention in the morning session. We're moving now to technical challenges for presenting the work happening in individual team members groups. From our group, I would like to introduce Aditya Gahlavat, who has been with us for the past 8 years. He's a senior research scientist in our lab. The last 4 years, he has dedicated to development of this theoretical analysis of using deterministic L1 adaptive controller with learning-enabled components that come, for example, from computer vision. With that, I would like to let Aditya take over. There is a big major paper on archive with 141 pages that formulates this theoretical foundation for this rigorous work. So we can test deterministic controllers with machine learning algorithms coming from computer vision that are doing instantaneous reference generation. And we can verify it theoretically, it's proven theoretically, it's not empirical verification. It's not we throw it into simulation environments, Monte Carlos, and say, oh, it works. And now we have a rigorous foundation for that. Aditya, take it over and it's all yours.
Sorry, just a logistical thing. If you have a question, just raise your hand and we can bring a mic to you. So you don't have to stand up and.
Thank you, Naira. My 15 minutes are, that does not count. Okay, I need my 15 minutes. Good morning, everybody. So yeah, as Naira was saying, we're going to talk, at least in our group, the work on trying to merge machine learning with adaptive control without having to change anything about machine learning, using it as it is and what we can do. And trying to also make analogies with the things that we understand. So conceptually, the language might change, but conceptually the things remain the same. So one of the things as we move forward, especially with the use of learned components, is that our nice structural things that we had, for example, certified reference trajectory generation, gain and phase margins, etc. They, if we want to use machine learning, they need to be a little bit loosened. However, that comes at the expense of the problems of certification and the guarantees of how does my system perform given the model that I have now? Do I need to learn on the fly? Well, I might not have the data or the compute sources. So we need to move slightly to a different language, which hopefully I will try to convince you today of doing. So looking at a very prototypical autonomy pipeline, we have our sensors. The planner then uses that representation to send downstream commands. And then we have some low-level controller for trajectory tracking. Now the questions, and these questions are general, they are not related to machine learning, but they are equally as important and to get their answers is a struggle. So questions like, what if the autopilot cannot deliver what the planner asks, of course? And can the planner account for the capabilities of the downstream components at the plan time? Because without this awareness, we run into issues of course, lack of certifiability and unpredictable operation. So we need to figure out how can these things be communicated with each other in the system, and what should be the content be using that language if we are going to use machine learned components. So to do that, we have to see what does the ML things provide us in the very general scenario. So what do we get? Well, a very standard prototypical ML pipeline is you search for a best model within a model class that fits the data best, and which is the same as minimizing some loss function. So what you get at the end when you say I'm satisfied with my learned model is this model risk, which is the loss over your training data. This is the only thing that your learned model is saying. It says that if you ask me to operate on the conditions that I've seen before, this is what I will do, and that's all and nothing more. Okay, and the main thing about this is that this guarantee, what your neural network or any other model is saying in perception or in controller or dynamics, this guarantee depends on the distribution, and that distribution is exactly what your training data is. So again, the performance that it guarantees is based on the training data. So if we want to ensure that our, say, a perception model works with a certain guarantee, we need to be able to also provide two things with respect to, which is what was the loss function that you got when you were satisfied with the training, and what was the data that you trained on. This dependency on the data usually is not considered, which is an important question, because I might have the best algorithm, but if I don't have good data, it does not help me at all. So with the language of distribution, we are going to now pose when uncertainties in the system come in as a problem of distribution shift. So uncertainties in the system, we always have some sort of epistemic uncertain model errors, simple. And then we have some unlearnable but statistically known disturbances like wind disturbance and truly random stuff. And combined, they make the system behave like we do not expect to see. Again, a very standard problem, but we can cast it as a distribution shift problem. Now, to be robust to such things, of course, you can be like, if you're doing parametric estimation, is to like run more time in the wind tunnel, get more data. So of course, you can do that if your systems are cheap to evaluate and you do not mind if they fail from time to time, then it's fine. But when we come into high consequences systems like aviation and say interplanetary exploration, well, now we don't have that luxury to bash the system into the wall repeatedly, get the failure data points, and then be happy that I have seen all possible failure modes, and therefore I'm robust. The challenge is here, we have to be robust without having to see that. So it's like a generalization problem, but from a controls perspective. So what we want to do here is to look at the systems that are generating the data. Because from a controls perspective, that's what we do. We manipulate the behavior of the system in certain ways. And since my data is a representation of what my system is doing, by controlling my system, I should be able to get some notion of where does my system distribution lies in when I run it. So I'm changing the system that is leading to the distribution. I'm not touching the distribution, purely doing system theoretic analysis and control. If we can do this, well, the good thing again, the data is where all my learned components are guaranteed to operate in some way. This is what they say. So if I can make sure that my data is around where they will learn, I will start to get some notion of, oh, I can use them without asking them, the learned components, to do anything addition to what they already know. So for that, we devised this control strategy. So this is, I won't go in the theory, just the results of it and very high level points. So we did the L1 adaptive control, but for certificates in the sense of distributions, probability measures. And we were able to consider a much general class of dynamics, which are stochastic differential equations. And these are nothing. This is a pure generalization of ordinary differential equations. So if you were to turn off certain things, you get your nice ODs back. And in that way, this will be a pure generalization. And like the uncertain systems, we have uncertainty in both drift and diffusion, where the uncertainties come in, and these are epistemic. And we also have this addition of this Brownian motion. This represents natural randomness that your system might encounter that you'll never be able to model, regardless of how much data you get. So it's like a coin toss. You can get as much, see how many times you get heads or tails, heads or tails. The next time you will never be able to predict with 100% probability. That's the thing. But you know the distribution of it, it's 50-50 uniform. So we take the standard L1 architecture and we just apply a different analysis to that. So L1, as some of you know, has our standard paths, and we maintain our controller identical. The controller implementation is identical to how it has always has been. So it maintains the certifiability on whatever system it was certified on. The stochasticity is just inherited because it's controlling a system that has these features. And a very, very important property of that is that our implementation is a standard. It's in the feedback space. So you operate like a standard controller using state or output feedback. That's all you're getting. But the guarantees that we are getting is in this distribution space, which could be if you were to run your system 1,000,000 times, that will give you a distributional behavior of your system. Now we want to get those guarantees without having to run the system millions of times. Because when you're running the controller, we only get state feedback or output feedback. We're not getting multiple data points. So just keeping our feedback space separate from our distribution space, which is a very novel dichotomy between these two. So very quick going over the, what's the time? 10 minutes? Okay, perfect. So just quickly, the guarantees, and again, just to show that we again retain our uniform guarantees, which we will then use later. So we get uniform guarantees in the sense of Wasserstein metric, which is a metric between distributions, and it has nice properties that I will discuss. And we also get these high probability bounds. So if instead of wanting distributional certificates, you wanted to see, will my system be safe with a high probability, then you use these pathwise results. And we'll use Wasserstein when we want to introduce machine learning components. And the good thing is, again, so they have one-to-one bijective mapping to deterministic scenario. Okay. And there's some changes that happen that even if you have no uncertainties epistemic, your systems will not lie on top of each other. This is because of the noise in the system, the Brownian motion. It's again, the heads and tails will always be different, even though they're the same distribution. And the generalization part, if I were to turn off the stochasticities, I get back my OD and my results become again back into my Euclidean space. So it's a complete one-to-one generalization. And for the high probability results, we have a very good property, which is these polylogs. So the idea is that suppose you want a system to be certified for a very high degree of safety. So suppose you accept a failure probability of 10 to the power minus 10. Okay. So given that, your controller will say, okay, as long as you're in this set, I can ensure that you will only leave the set with a probability of 10 to the power minus 10. That's a very high probability, high consequence scenario. Now, what these bounds, because we have in the log, what that means is these bounds get tighter and tighter the more you are going safe. Because you can end up in a pathological scenario, which is, for example, if you're walking outside and it's icy on the sidewalk and you want to be very safe, well, a pathological answer to that is that you just stand, you don't walk. But then that is not helpful for us, right? So it has to be usable and non-conservative. So because of these, if I were today, for example, a probability of 10 to the power minus 10 of, say, unsafety, these polylog bounds give us an order, 3 orders smaller than what we would get using a regular controller. So that makes it very tight when it comes to usability for uncertain systems. And there are no results like we have similar results for known systems, but not for uncertain systems with control in the loop. So a very quick numerical simulation we did for angular rate dynamics of a quad rotor. So on the left, we have the uncertain and certain system. So the left is without a controller. And so we are plotting the 2D distributions and then the marginals on their X and Y. Now, this system, the blue one here is without our L1. It is not unstable in the sense that we think it is not diverging in its behavior. It's just expanding out. It's just the variance is exploding. And on the right-hand side, we see the green one with the L1 comes and tries to sit on top of the distribution that we need. And I will talk about this, the Wasserstein importance in the distribution shape matching, which will come when we do covariance steering. So we come back to our autonomy pipeline with the questions of what should I communicate, or what should the components communicate, and in what language, so that they can talk to each other without having to constrain themselves to a certain operational limit. So what what our approach is coming along is that for our low level, we use our controllers, obviously. That enables that the content that I communicate, at least from the planner from my low level control to the planner, is my planning bound, this guaranteed uniform bound. And of course, the language is in the space of distributions. Okay, so the planner knows that whatever it asks the system to do, uncertain system, the uncertain will remain around it in the sense of distributions, which then is such a general concept that we'll be able to bring in many things like perception and machine learned components. So we do this for a covariance steering, which our previous speaker had talked about, but this is more on a development level. So like any optimal control, when we have our systems difference, of course, the problem happens when our system is not like what we behave, which is very standard, except here we're talking in the space of distribution. So what we can do is, of course, make the problem robust. We minimize the worst case effect. Now here it is a minimized worst case of a set of distributions that a controller is guaranteeing. Getting that is a challenge, but of course we have a controller, we can do that. So to get this challenge, to get this ambiguity set, we use our L1 controllers. But usually, if you don't have such a strategy, you have to rely on certain assumptions that are not realizable. First is, of course, that you have seen the scenario that you're trying to be robust against, which is, again, you have all the experience in the world, so you'll make smart decisions. We don't want that. It is limited. We have limited experience. And further, properties of the systems, like known bounds. How does the system behave a priori? Is it bounded in certain moments or not? These things are, they become too restrictive. And if we want to maintain the usability, we don't want to add anything at all. So we do this for covariance steering. And this is our guarantee that a controller is providing, which tells the planner that, planner, whatever you're doing at extra, the actual system will remain in this set around with a radius rho. So the planner is like, okay, I'm going to plan for my extra, but I'm going to ensure my constraints satisfied for the worst case in this ball. And this way, your system operates with a guaranteed safety margin. So we did this for covariance steering. This was done with by postdoc Vivek here. So on the left-hand side, you can see without L1 again, yellow is our covariance steering nominal. Blue is our actual system. So because the planner does not know, it sends the reference commands to the downstream. The system tries to follow it, but you can see many paths collide to it. And the nominal is doing something interesting because it is covariance steering. It is not just squishing down the variance. It is shaping the variance. So to go through that narrow slit, you will see that the yellow is not just uniformly squishing into a circle, but is squishing into an ellipsoid so that it can slide through. Now on the right-hand side, when we put our L1, the bounds are conservative, but the planner knows that, okay, as long as I keep that margin, my system will remain safe, the actual system. So now the planner takes a longer route, but the system follows it quite faithfully. And the squishing of the covariance comes into effect because we are tracking in the sense of Wasserstein, which is not talking about where the distributions are, but what their shapes are also. So these are true metrics in that sense. So you can see on there, so our yellow, this actual system is Gaussian, the nominal system. My true system green is not Gaussian, but my controller takes by those distributions there and try to match the shapes as much as it can. So it is matching both in location and shape. So when you're using a controller like covariance steering, which is squishing and shaping your covariance to move through the obstacle field, the controller will also try to do that and not just compute the worst case as in, say, total variation distance. So with this, then we extended it to how do we include now perception uncertainty in the loop as well. We have our system uncertainty. Now we want an environment uncertainty. To do this, we broke apart our problem in two parts. That we usually have sensors that send us data, and then we have a model, say a convolutional neural network, that maps it into a representation that a planner uses. So you again have that dual sum of what was the data that you had and what was the model you trained on. You need both of them. So in this work, we just divided into like, what was the data that you had? So you had some finite amount of data. How does that affect your performance and what guarantees you can get. So if you trained your environment model on 10 sample points versus 1,000,000, give me a bound based on the number you have. So we assumed our finite samples in this for using which we develop an approximation. And again, our environment is not like what we approximate because we only have a finite samples. We've not seen everything. But we are able to, for our environment uncertainty, use certain, these exist with the Wasserstein concentration bounds, which says with the number of samples that you have, you're guaranteed to remain in a set around the actual thing with certain probability. Now that comes in again, because so general, it comes in the sense of ambiguity sets of distributions. We already have sets of distributions on a low level controller. So now we can combine them as a direct Cartesian product to get an overall uncertainty ambiguity from both my upstream perception and my downstream controller. And the planner, if it can account for both, which it should, because it only needs an ambiguity set, we just have a larger ambiguity set, we can be robust now both to perception errors and the low level control errors. So we took our original Wasserstein set and added my downstream, this is what L1 is providing, and then took the Cartesian product with my environment's finite sample based uncertainty in my perception. And then we just sent that combined ambiguity set to my optimal controller problem. So it's an extension of what we did for covariance steering. And then we were able to get these results. So here, my yellow is my nominal, which is uncertainty free everywhere. My green is with my environment and L1 tackling the uncertainty. And the red is just running in receding horizon. It tries to do its best, but it does not have the knowledge of my ambiguity sets. So it is doing the best it can. So in the first scenario, you can see that the red is it is safe, but before running the experiment, we could not have told you it is safe. So there is no certifiability that way. It is unpredictable. In the second one, again, because of the unpredictability, the unknown system just collides with the obstacle. And you'll see here it collides. The red will go here. There we go. And in this case, again, it tries to avoid the obstacle because it's running in receding horizon. So it is getting environment feedback. But as soon as it goes there, the uncertainties are so strong at that point, the uncertainty overwhelm it and it just goes away. So this is how we brought in our, the perception, the half of the perception. The next part is to actually bring in our convolution neural networks or encoders, and especially to run it on baseball avoiding multirotors to set it as a common simulator, if we can do that on there. And just a couple of works that we already had with using machine learned components directly with adaptive control was this done with Sandeep here for our last SciTech, which was imitation learning, where we were discussing about when you have a simulation to real gap, sim to real gap, that is our epistemic uncertainty. Sure, the controller can take care of it, what we have. But when you're learning a controller that is copying from an expert, then you have this another source of error, which is this policy shift. That is, my learned controller was not as good as my expert, so that will cause a distribution shift. So we did this dual part where here we used an approach that is robust to policy shift, as work done by Nick Matney at UPenn, and we then applied L1. So dual, we could do imitation learning on fully uncertain systems. So the two sources of uncertainty. And these are preliminary results, and right now we're working on extending them to more serious systems and with the theoretical muscle behind it. And finally, this was at 2024 ICLR when we robustified model-based RL without touching the model-based RL. And in the sense that any learning RL, it's not learning a model, it's learning a representation that it thinks gives you the best output. So just using that as a model, what we could do, and we took a state-of-the-art algorithm, and we were able to show that having an adaptive controller in the loop used smartly without changing the upstream. That was a condition. Do not change the upstream. So whatever you train, just slap this on and it should work. And yeah, so we got mostly better results. And this one is my favorite because the left one without L1 actually runs like my dog in the evening when she's tired, just flips on, falls onto its side. There we go. And going forward, talking about the framework that we are interested in is following from our first speaker that we had, where we are keeping this safety and learning decoupled for performance. So the online part is where the safety is happening. It is using what we already have. So you have the models that you had, you design your controller with guarantees, and that is going to give you that, I'm going to say guarantee a performance of some constant. You decide if it's good or enough, or good or not. The learning happens on the side that you may get good collect data, you may learn, you check if it's good enough, and then incorporate it. However, we do not want this learning to be happening at the real-time control loop frequency, because even if you have the compute sources, if you have a bigger vehicle that has compute sources, you may not have the data. You may not be, your control mission might not take you to places where you need the data to learn. And so again, it's the problem of you need a good algorithm to train, and you need good data for it, the good food for it. And from a safety perspective, we do not want to have this dependency that, oh, you need to learn fast, only then you'll be safe. So we decouple this. So our safety remains persistent, but our performance based on learning is opportunistic. Whenever you can do better, do it. I'd rather be conservative and safe rather than 50% really high performing, but rather 50% just falling out of the sky. So we want to keep that baseline guarantees. And so this was another, the full framework that we are working with the students of, using both the learning and the exploitation, exploration and exploitation, that now we have brought at the same level, because we are using every component is talking in the space of distribution, in the space of probability measures. So we have a planner that takes in these probability measures provided by the controller and perception, and then designs plans that are robust to it. And so this is a long going process, but we are getting quite far into this. And thank you.
Thank you, yeah. So question, the slide where you're talking about offline and online learning, right? And I'm sorry, what's happening online, what's happening offline. So I'm with you. I absolutely agree that you don't want to be falling out of the sky even 10% of the time because you don't have the data. Have you given any consideration of what I would call opportunistic learning, which is online, but to do so, you almost need to understand where you are good and where you're not. And so potentially you can exploit that area where you know you're good to get better performance.
Yeah, that's an excellent question. And I will show this. So this figure did not clearly show that, but yeah, what you are asking is, so in this figure, I'm showing that these red dots, which are fading out, these are the data that we already have based on which we have the models. And now this is my planner taking the system with this tube of distributions through. So if we want to learn, you can have a trade-off where this will start to push it towards the edge of these data boundaries. And you can see, oh, if I'm this close to the boundary, I'm still acceptable. There's an increase in risk, but I can compute how risky I am going. And then you can be like, okay, I'm comfortable with that risk. Let me go to that boundary, collect more data, and then expand these data sets out and out. That is definitely would be a good way to use it. And we hopefully do this to make it. So there's a tuning knob. So you make it more risk seeking for learning. So robust exploration, or risk sensitive to safety, you make it risk averse. So risk seeking and risk averse.
So if that works, if you do an implementation exploration, what I have in mind is more of not so much that you're going to be doing specific planning for exploration.
Okay.
But you are taking advantage of the data that comes your way, whether from your own or from other sources. And this is going a little bit to what we discussed earlier in terms of where things are going in the outer loop and decision making.
Okay.
Does that make sense?
I think so. So I'll just repeat and you tell me. So it is, we are flying about, we are collecting data. How can we use that while flying, I imagine? Or yes. Again, so we have work where we had taken the deterministic system and we had a ML model which did exactly that. It was just asked to do obstacle collision avoidance. And while doing so, whatever data it collected, updating the models. Now, of course, it was in simulation. In the real scenario, I would imagine, based on the compute resources you have on board. So if you have a capability to do that, absolutely. And the method that we are developing here, it depends on, so we need to figure out if the model learned is good or not before putting it in. And the way we are doing it, we are just saying that, okay, you trained a model and you stop the training when you say the loss is acceptable at your training. Anybody who does ML, they just stop and they say, oh, this was my loss at that. So that becomes for us, because again, it's defined distributionally. So we get that loss, we can determine if that is a good model to incorporate now or not, or we should keep it aside and keep it updating it as the data is coming on. Yeah. And that brings us that just requiring the ML part to just say what it is designed to do, nothing more, no Lipschitz continuity or like, hey, I'll be good. Just give me the loss at the data you see, then I will decide if it's good for me. So if you're flying about and you get the data, you learn it, absolutely. So you have that, what do you say, that phrase of testing something, if it's good or not, and then include it or keep it till it improves.
Information may not be just something that you have, but information that is coming from the outside.
Yeah.
To give you a better understanding, so you want to be able to exploit that. And then, of course, there has other domain implications for what. Okay.
Absolutely, yeah. Especially the fun domains, I would say, lack of other word. But yeah, definitely. This does open many directions, and we are trying to cover as many. But yeah.
Thank you.
Thank you for the question. Youngjun.
Question was maybe you need to know to use this. Maybe you need to know the strengths of the disturbance over noises, and then do you have some idea how to?
Yes. Again, a great question, right? Because we want a certification of robustness, but it can't be arbitrary, right? So like in regular system, you say that your uncertainties which are causing this difference of actual versus what you think, it depends on, say, the growth of your uncertainties. So like the growth bounds, so Lipschitz, locally Lipschitz bounds on things. So these things determine how strong your disturbances are. And then things like how many of these disturbances you can actually counter, because they might be sitting out of the control channel. Then you have to just be hope and pray that you're robust against them. There are advanced strategies for that. But definitely, these bounds, they have the dependency of the disturbance that you're countering and what you have trained. Absolutely. They will break if you make them unreasonable as they should. If the situation is good, disturbance is less, you should get a smaller bound, as you learn, for example. But if it is bad, you should get a large bound, and it does exactly that. Start the timer.
Okay. Now we will have our next talk, which would be a hybrid mode. So we'll have a speaker here, and then there will be a speaker on the Teams call who will be presenting. Let's see, Michael, if you are able to share your screen. Okay, perfect. Can you try putting it in
yes,
full mode? Yep. Okay, and then let's see if we can. Okay. All right. So for the next talk, we have Professor Luisha and Michael on the call. And in this talk, I think they'll share their the ongoing work and the work they did in the ULI project on certifiable and safe use of learned components. Professor Shah is a leading expert in safety integration of time critical components in cyber physical systems. He's been on a lot of committees, and he's also led development of codes as well. So we are glad to have him on board and hear from him. Professor Shah.
Can you flip the? He's going to. Oh, okay. So I want to give a little bit background. About 2 decades ago, the computer control become widespread used. Then there are problems surfaced. The software fail rate caused by bugs is more than 10 times of the hardware fail rate. And the trend is going the wrong direction. So the National Academy of Science convened a team of experts, and I'm one of them, to say, can we really verify end-to-end? The most important thing is, can you verify the binaries? The source code does not fly the airplane. It is binary flies the airplane. So the binary verification, formal verification, is very, very hard for a complex controller. And the software will become more complex when we try to improve performance or minimize the performance loss function. So it looks like there is a gap wider and wider. So under that background, committee was established. And as you can see, there's a booklet was published. The published booklet is looking at all the major software failed, the reliable ones, and the failed ones, like the 3 Mile Islands, and what actually worked in the real world, not on the paper. Not just on the paper, I should say. First you have something work on the paper, and then you make it work in the real world. Like as we all know that. So I highlight the conclusion in the executive summary. One key to achieve dependability at reasonable cost is a serious and sustained commitment to simplicity, including the simplicity of critical functions and simplicity in system interactions. This commitment is often the mark of true excellence. There are no alternatives to simplicity. Advance in technology or development methods will not make simplicity redundant. On the contrary, they will give it greater leverage. So that conclusion basically led, or actually already developed a simplex architecture. The idea is very simple. You use what the technology at current point can verify and validate in flight. We have a lot. We can fly the airplane certified. But all of those are low-dimensional models. It captures the essence of the airplane behavior, and we can certify it, you can fly it, and in fact, the airplane is so safe that we are not willing to buy insurance anymore. So the idea is, how can we create a variable sort of a stability envelope, the leader power function under constraints. As we fly, the self-constraint changes. So the envelope, like the previous speaker, you will see the leader power function, the shape will be changed so that you can think about the aircraft is always flying inside a leader power function, which adapts to the environmental uncertainties. So it works for a while until people put it into real world practice. And then they said, simplex works well only in nominal conditions. The airplane sometimes will have, let's say, partial engine loss power, or aileron partially stuck, or air accumulated on wing. So your Leopold function have not anticipated that. What are you going to do? And they're so fast. Then that frustrated me for a long time. I said, what should I do? I need somebody who really knows how to do adaptive control that's robust. So I look around and find there's a person called Professor Naira Puvakinyo. I said, where is she? at that camp in the mechanical engineering department. So I call her up, and then we actually developed something called L1 simplex. Essentially, it brings the fault tolerance. They can handle the software fail, RP3 software, and a lot of disturbance. So then the NASA program came. They said, we rely on perception. We want vision guide. But if the vision is totally wrong, safety is a joke. So I said, okay, we'll work on it again. So we developed what is known as a perception simplex. The perception had two sets. One set is called physical safety. That's a collision avoidance, a fancy word. Another one is law abiding, law compliance with the law. It says there's a stop sign. Well, okay, or you have to stop. You cannot say there's no other car. So physically speaking, collision is impossible. You try that, you know what will happen. Your license will be suspended. Okay, so there are two sets of safety, regulatory safety and physical safety. Now, I'm not going to go into many details, so I will let Mikhail. He is a graduate student. He's currently and tell you the more details. I think that I always like my graduate student who does most of the work and has the visibility. On that note, I will pass over.
Thank you, Professor Shah. So can everybody hear me? Well,
yeah, we can hear you. Go ahead.
Okay. Yeah. So first of all, briefly, I apologize for this remote presentation. I had to be in a remote mode for certain circumstances. Well, I'll continue from here, and I'll briefly outline the structure of the remainder of the presentation. I'll first summarize our completed work, focusing on perception simplex at the end, and then I'll discuss ongoing and future directions that build on it and which have mainly stemmed from this ULI project. I'll start with the neural probabilistic circuits, which were led by my colleague Simon Yu. And this work aims to improve neural network reliability by decomposing predictions into meaningful components. For example, instead of directly detecting a heliport landing area, NPC detects its defining parts, the circle, the letter H, and the white and yellow color patterns. Under the ULI program, our team, led by Professor Bo Lee, also developed SafeLander, which is an architecture that leverages state-of-the-art AI models to make the landing process of autonomous VTOLs, such as Guam, more robust, helping avoid collisions and other unsafe scenarios. To enable fast and safe testing of ideas, we developed a high-fidelity realistic simulation framework based on the Carla Autonomous Vehicle Simulator. Our framework, called Air Taxi Sim, supports vehicles such as Guam and Minihawk, developed in collaboration with other ULI teams from UNR, MIT, and more. And here we have an example landing scenario simulated in Air Taxi Sim. I'd like to mention that it is already used by several teams across universities, which is quite good. Now, I'll move on to the line of work on perception simplex that Professor Shah has already mentioned. And this work originally was led by my former colleague, Ayush Bansal, under Professor Shah. And from now on, I'll occasionally call perception simplex PS for short. And put simply, any autonomous vehicle equipped with PS can avoid collisions caused by ML obstacle detection failures, as long as the stated assumptions hold. And the assumptions are outlined in the paper, and they are not super restrictive. They are quite practical. And perception simplex works as a runtime assurance algorithm. The safety layer, based on LiDAR, monitors and can override the actions suggested by the machine learning perception system. Well, to enable the guarantees provided by PS, the system relies on a key algorithm developed within the ULI project that is called verifiable obstacle detection. It uses classical geometric methods with LiDAR data to detect obstacles. And the key idea is that when the angle between two points from consecutive LiDAR rays exceeds a threshold, the latter point is classified as part of an obstacle. These points are then grouped into obstacle detections using simple explainable 3D clustering methods. And in validation experiments, we observed that practically no obstacle was missing. Let's now move on to the current work, which is motivated by the fact that perception simplex can be overly conservative, especially at high speeds, which can limit performance. After all, the safest vehicle is a stationary one, but that is not practically useful. To address this, we developed synergistic simplex, or SS for short, which is an extension of perception simplex. And the key idea is to carefully break the traditional rule of not using ML information in the safety layer. By incorporating selected ML functionalities into the safety layer, we improve performance without compromising safety. And this direction continues to draw interest from former team members. This is something I'd like to briefly mention. Ayush, for example, who originally worked on perception simplex, remains a valued point of contact for, continuity of knowledge through occasional discussions. Right. Let's now move on to rather the future research, which primarily extends the synergistic simplex, which we just discussed. Our future research has 3 research thrusts and 1 engineering thrust. So thrust 1 improves synergistic simplex for static obstacles. This is an assumption we have so far. We assume the obstacles are static. In thrust 2, we remove the static obstacle assumption and study when safety guarantees can still be provided in this dynamic setting. In thrust 3, we look at extending the safety envelope in dynamic settings even more. And finally, the engineering thrust supports this work through large-scale simulations, building on our simulator development experience from ULI. And I'll talk about it a bit in more detail later. I should also note that the synergistic simplex applies to almost any cyber-physical system, including both ground and aerial vehicles. And most examples here use ground vehicles simply because they're easier to explain and have more mature regulatory frameworks. I note again, this is more like future research. So here is an overview of synergistic simplex in its current form. And let's zoom in on the core contribution of this work, the ML to safety layer link. In thrust 1, we aim to introduce a coherent set of filters to screen out clearly incorrect ML outputs. Well, using these outputs does not weaken the formal safety guarantees as shown in the paper. Filtering them out is still beneficial, and that is our goal here. One possible filtering approach, for example, is to use physical counter evidence to validate ML outputs. Let's say the ML model detects a green traffic light, but we do not observe any intensity in the green spectrum. So we can discard that prediction. And we plan to implement this as a series of Swiss cheese-like filters, allowing only reliable ML information to pass through. And the objective here is not to extend the safety envelope, but to further improve the performance of synergistic simplex. Now, let's turn to thrust 2, where we aim to extend the safety envelope of synergistic simplex by removing the assumption that all obstacles are static. So on the left, we see how synergistic simplex currently models the world in the context of autonomous ground vehicles. And on the right, this is the behavior we aim to achieve with dynamic synergistic simplex, along with formal safety guarantees. Okay. But in its current form, even though synergistic simplex is less conservative than perception simplex, it can still be overly conservative when dealing with moving obstacles. For example, on highways, as shown on this little animation. And our goal is to address this. And to do so, we need a reliable way, not a computer vision based one, RGB based one, but a reliable way to estimate the velocity of surrounding obstacles, which is where FMCW LiDAR comes in. And this video here illustrates how FMCW LiDAR differs from conventional LiDAR. Unlike standard LiDAR, which measures only distance, FMCW LiDAR also provides the relative velocity of each detected point. And I want to note here, it does not give the full velocity of that point, since the tangential component is not observed. But the radial component can be sufficient to extend synergistic simplex to dynamic environments. Now, let's talk about thrust 3, where we aim to expand the set of verifiable components in the safety layer. And we start with verifiable lane detection based on LiDAR to extend one of the current applications. And this builds on a useful property of LiDAR, that it returns different intensity values for road surfaces and lane markings. Again, this is an example based on ground vehicles, something that we all know very well. But we also plan to integrate other verifiable components, such as HD maps and logic associated with HD maps, for example, how to break the road into lanes without actually detecting lanes by simply knowing the number of lanes on the road. And this will further improve both safety and performance. Now, in this slide, I want to describe an interesting way how we can extend the safety envelope of multi-simplex systems in an interesting way. It's not novel in mathematical terms, but it's quite interesting in the context of simplexes. And on this slide, we have the ML faults shown in this Venn diagram, with the obstacle detection faults on the left, lane detection faults on the right, and cases where both fail in the middle. Now, perception simplex covers this region number 1, which is this region on the left. So we have safety guarantees for this region. If we develop verifiable lane detection, we're going to cover region number 3. And at first, combining the two might seem to cover only these separate regions, but in fact, we'll also achieve coverage of the overlapping region, the case where both components fail. And this kind of super additive properties is what we aim to leverage to further extend the verifiable safety region of synergistic simplex. And now I'd like to turn to the final thrust, the simulation infrastructure for realistic evaluation. Existing benchmarks such as Carla leaderboard and air taxi SIEM that was developed on the ULI project are useful, but focus on short scenarios. They do not capture performance over hours of operation. And long horizon simulation would let us measure the practical cost of safety algorithms, such as reduced speed in real fleet operations. And for companies like Archer, Joby, Whisk, Waymo, and Zoox, this reduction in speed and therefore revenue can be viewed as insurance for guaranteed safety. And to support this, we plan to build 2 Carla-based large-scale simulation platforms, one for ground vehicle fleets and one for aerial fleets based on, air taxi SIEM that we developed. And these platforms will help evaluate dynamic and filtered synergistic simplex in realistic operational settings, building on our ULI experience in simulator development. And this video here illustrates what the autonomous ground vehicle fleet simulator could look like. While Carla leaderboard that I just mentioned focuses on evaluating performance in specific short scenarios, our goal is to move beyond that into long horizon simulations. And finally, I'd like to conclude saying the ULI project has led to a lot of significant milestones, and the research directions we explored have also opened up several promising ideas that we are very excited to pursue and that I've briefly touched on. Well, not too briefly, but I've touched on in this presentation. I'd like to thank you for the opportunity to present, and I'm happy to take questions.
Hey, Mikhail, this is the questions table. If I understood you correctly, you said when you guys were testing the simplex in the sim, you were detecting obstacles, but it was more empirical rather than theoretical guarantees. Did I understand you correctly?
Almost. The guarantees are theoretical because we are based on our algorithms are based on LiDAR, and given proper operation of LiDAR, we can derive theoretical guarantees. And these guarantees include some assumptions, such as absence of fog, for example. So in fog, we would struggle to provide guarantees because LiDAR might not operate properly. But if we are operating in clear weather, where we have certain models for LiDARs, where we know how well LiDARs operate, we can provide theoretical guarantees, which then translate into actual empirical results, which fully correspond to the theoretical guarantees. So the guarantees are theoretical.
So let me follow up on that. Is there in your theoretical development, is there a way to characterize the performance of your sensor system, how well or poorly it is giving you information in that particular condition? Does that make sense?
By saying characterize.
So what you're saying is that if LiDAR works properly, then we're good, right? So is there a way to introduce that uncertainty about how well or poorly, let's say, LiDAR gives you that information and incorporate that into your basically theoretical guarantees?
I see. So we haven't considered specifically how, let's say, noise in LiDAR can affect the results. Or I should say the obstacle detections. But thinking about it in retrospective, I would like to avoid making solid statements, but I don't see how it can break the architecture. So it's not fragile to, some kind of noise. Obviously, huge noise would break anything, but reasonable noise, I don't see how it could break the architecture.
The answer on this question is, here is the signal to noise ratio for return. Good quality LiDAR's noise is not an issue. It's the return and fog or heavy rain, that's the issue. So when the signal to noise ratio summarized over area region or object drop below threshold, we have to admit we don't have that. And we take other safety measures we can. So yes, the safety at the end of the day always depends on sensor. The sensor totally fails. We don't have redundancy. We can fail. Okay. That I think is the answer.
I have a follow-up question, but I agree if you want to continue.
Yeah, my only other question would be, if you, as you translate from LiDAR and ground, you get to air and different set of sensors, do you have any thoughts on how you would modify and or incorporate some of the different conditions? That's right, you don't have lane markings, you have some other stuff that you're looking for. And depending on your flight condition, whether it's other aircraft or when you're landing on a runway that starts getting a little bit different, right? So have you given it any thought yet?
So I'll try to answer that question. So I guess the short answer is the simplex doesn't change. It applies in the same way to any system. And to some extent, the aerial systems can seem even easier for simplex. Now, I'm not saying it in a negative way, but rather in the sense that you don't have the proximities of obstacles that you get in ground operations. So speaking of different a different sensor suite, we are trying to explore different sensor modalities. And again, the ground application is just an application. So we are trying to stay agnostic to the actual application of the simplex. So it is applicable to ground, it is applicable to aerial, it is applicable to, I guess, submarine. Just thought about it. So yes, it's just a matter of, modifying your fault handling algorithms. On the ground, you brake. In the air, with a VTOL, you might try to hover immediately, change to the copter mode and hover. Does that answer your question?
It does, thank you.
So I'm going to attempt to break the winning streak of the question table by moving the questions over here. First, actually, I would love to understand now, how do you pronounce your name? Mikhail.
Yes.
I really like your Swiss cheese model, and which makes sense. Like, if you have something that's wrong, you go check something else, and 2 or 3 things are like obviously, it's indicating something else. Now, do you have a formal way of prioritizing which filter first, or ordering the Swiss cheese filters? And the second question I have is, you have what is the representation you use in order to reason about the capability of a particular component perception or something like that? So it's two vastly different questions, but I'd be happy with the Swiss cheese one, and then I can probably go read your paper to understand the second one better. Thanks.
Sure. So this is a technological bottleneck. I did hear the first question properly, but the second one, I will ask you to repeat again. I can try and answer the first question now. Yes, we do have an ordering. Because it's still, research in progress. I can't name it off the top of my head, but we do have an ordering, and it goes like approximately like this. If we can construct this, so it's a 4-step approach. If we can construct a simplex for the ML information that we are using, let's do it. Right? We can come up with a, verifiable twin of that functionality. Let's do it. Then, if we can confirm what the ML layer is, sorry, the second step is deny. No, it's confirm. If we can confirm what the ML layer is saying using physically meaningful data, that's good. We pass it. Third, if we can deny, so there's actually a difference between the second and third. I'm not going to go too much into detail, but if we can deny what the ML layer is saying, that's sort of the third step. And the last step is we can neither, approve it or deny it, or we can't come up with a simplex. That's the case where we rely on the ML layer's own confidence in its prediction. So it's sort of like going from the most rigorous way of filtering it to the least rigorous. And the second question.
Don't worry about the second question. I'll read your paper to understand better. Thanks.
I want to make a comment because you heard about the simplex thing. So does it really work in the real world? So what I want to say is a very interesting coincidence. First of all, I noticed if the ASTM international standard for UAV software safety, it codifies simplex architecture, but in a very sort of general way, just a requirement and not allowed to refer to any specific solutions. But that's the bureaucracy of every standard. The most interesting thing is who wrote the standard, made big part standard. That's Suraj sitting right next to me. One of them. All right. Okay. So in some sense, the simplex, because this is a consensus, it's an international consensus. So it's really moving from theory into practice, not only individual practice. At least the Russian company is using and zero surveillance. Okay. In fact, it's right to lots of research paper and supplies zero the standard paper. So now, given the situation, NASA really cares and put it into practice. So transition practice. The best way is to go through a reference architecture. And I should talk to Suresh. We have decided to do it. And the first step in our reference architecture is that replace the safety controller from the bus controller L1. So the battery control or whatever Suresh want to do, I would like to control expert to set what is the most robust battery controller dealing with the branch faults. The second step, the branch architecture we are going to address is the integration, or actually the further development and integration between the perception sequence and the relatively mature control sequence. Actually, there are several large projects already used there. Again, was reference. How well it works for the control sequence. Okay, so and then we will move towards the newer research called synergistic sequence. Account just present. Why the reference architecture is important? It turns out I made in my first phase in my career developing the real-time scheduling algorithm for real-time computing, and it becomes US standard, and then it becomes actually standard, it becomes international. All it happens, and then later on, actually, on the multi-core standard, they all have a approved and being used. So the key lesson is the standard committee only pin down the requirement, and they refuse to recommend any specific solutions, so that they will not sort of restrict people's innovation. And also they are afraid people, some company or some research, put whatever their solution, the standard, and everybody depends comply and becomes some kind of self-serving. So when standard came out and really popular, the reference architecture is a proven solution. Because people look at it and say, hey, I used it, but we didn't address next Y, C, or I give you a hole. So it becomes a community activity. Truly makes the open standard be a widely followed standard. So since I'm lucky enough to run the Jewish, he's the active member of the ASDM. I'm not concerned on this time. So I hope people can participate. Because only with community participation, then we can develop a robust and widely practical system.
I have one very quick question. You talked about the Swiss cheese model, you did the Venn diagram of blending sensors. Have you considered broadening this to non-sensor based models to be included? So I'll give an example, right? So recently, a commercial vendor crashed on the moon, there was a LiDAR issue, right? So, if you had, for instance, a LiDAR system, visual-based perception, and then you had a I'll call it a heuristic model based on your dynamics, right? The IMUs are another sensor, you know that information very well. So you can, compute, hey, based on my past history, here's when I would impact the ground. And the simplest model would be a timer system, right? That's done oftentimes in space systems, right? That, at this known altitude, this last known altitude, these rates, I have this much time until an impact, right? So can you blend this checking with non-sensor-based models? Because, that would be an improvement, right? I have multiple sensors, but then I also have models that I carry. Some of them would be sensor-based like IMU, but kind of tangentially, and others would be even more simple, right? Because that would be the best way to check across all the sensors. So just curious if you've considered applying it to other, I'm trying to loosely say non-sensor-based models.
I'll probably ask you to, could you please give the example again? I didn't really catch what you meant by saying non-sensor based system. So is it like a that's still a physical system, right? You're referring to.
Are you asking whether you could detect failures without by observing the world, for example?
Yeah, I kind of like that, right? So I have sensors, I have ML algorithms that use those sensors, right? Whether that's LiDAR or vision based, but there are other models that aren't necessarily so much ML based, right? They're more physics and dynamics, right? So I have a sensor and I knew that I'm going to assume is good, and I can propagate forward based on past history and say, I'm going to hit the moon, at this time, or even simpler models, which are just timer based. Hey, simulation table lookups that say, hey, based on this profile, I'm going to impact at this time, right? Can you incorporate those other types of models to enhance the Swiss cheese detection, failure detection?
Right. I think any model that is fully explainable and fully explainable by humans and understandable to humans can act as a sort of safety layer that we have in perception simplex. Perception simplex is simply, you can think of it as a cyborg where the safety layer is augmenting the whatever underlying mission layer, not necessarily ML layer. Let's move away from the word ML. Let's say it's a mission layer. And anything that is explainable to humans can act as the safety layer. Now, I think the question is, how much conservative is this going to make your system? Because that is what the safety layer does. It makes it conservative, and that is why we went into this whole synergistic simplex direction, where we are now trying to shave off all this, well, I guess bring back all this lost performance. So yes, I think it can.
Easy answer, Miguel. An easy answer is what you said before. Was an HD map. Now those maps, like the moon, space map, it's very useful. The moon is moving, but we know it's trajectory. So it's not changing anytime soon. Okay, so and HD map. The model in terms of can handle the constraints that's there. But no, let's say I can't suddenly show up in front of me, somebody jump on the street. So we have to use sensors. But even use the HD map, we also need to use something like a GPS. Otherwise, we cannot use the map. But if all the location sets are there, no location information, then the map is not useful because we don't know where. So the integration for static model, so what we really need to do is to integrate those static model and the classical method, and they are now probably following the idea on nearby calendar. We look at the ML as if it were the radar
dynamics. And then look at sort of what is possible space for aircraft to track based on the physics as a cone of reachable areas by the vehicle. So there's a lot of things need to be done, but the answer is yes.
Okay, let's thank our speaker.
Thank you very much.
The next talk that we have is also online and by Professor Evangelos.
Sorry, we're 45 minutes behind the schedule. There is an idea since the lunch is served, it's sandwiches. Maybe you can all grab the sandwiches, take 5-minute bathroom break or what. And we have working lunch. We just continue with presentations to be on schedule. This is everyone's last chance to be in this room with this team. That's why I want all the questions to be extensively discussed and answered. And instead of skipping and saying you can do the Q&A in a lunch break offline. No, I don't like these things. All the questions are openly, publicly discussed, answered. Grab your lunches, take 5-minute break, and we continue listening to the next online presentation of Evangelos Theodorou. He's also in Europe. It so happens right now we have him in Europe, but it will be impressive presentation.
Yeah.
5 minutes, grab your lunches, okay? Thanks.
Hello.
Hi. Yes. Yes, Professor. Hello.
Can I share my
Yes.
screen?
Hi. I can hear you well. Do you want to just try sharing your screen so that I can see if things are working? Yep.
Can you see my screen now?
Yep, they're up. You want to maybe do a presentation mode? Okay, perfect. Okay, this is good. Okay, and if I do, yep, perfect. And can you hear me okay? Yeah.
For some reason, I can hear me back.
Hear the back?
Yeah.
Back as in like echo?
I can hear. Yeah, I can hear
okay.
my presentation.
Yeah. Okay. Interesting. So just a quick question. So can you hear my echo or what is the other issue?
I hear an echo, and I hear myself too. There is a return back.
Oh, you hear yourself too. How would that be an issue? These all things are muted and I'm not sure if I can fix that from here because I have just one laptop set up and the system should be working, but in case if something, let's see.
Yeah. How about now? Yeah, I can hear myself too. Hello? Yeah, now I'm good.
How about now? Can you hear me okay now? Is there an echo still?
Yes, yeah, there's no echo.
It's better?
No, sorry.
Oh, it's
I
still
can
there?
hear myself too.
Oh, you can still hear yourself? Huh, interesting. Here, from there. Not super sure how to. So you can hear yourself on top of what I'm saying, right? That's the issue. Okay.
Yeah.
Let me see if I can get somebody to fix this. Yeah, I'll be like away for a minute. I'll be back.
Yeah.
You're not in that would be that you guys, how would you do that? How would you validate your stuff? You have actual hardware that really don't inertia. So that's the unit. So you can get for the first time, like started with infrastructure transfer. But then for the stuff as well, you're going to be able to distributions and trade. That makes sense. I think makes sense. I just think that that is more of we have the information on the concept and we have probably going on the information. We cannot take what we get on confuse me. This idea and I think that would be the way. I think that would be really powerful. I really enjoy you know, the demonstrations. So that's awesome. Yeah, so that was like,
Camera.
if we have a system that.
Can you hear me?
Yeah, I can hear you. Is it how I tried to change some things here and see if did it
Hello?
fix? Hello, I can hear you. Can you hear me okay?
Yeah, let me speak. Okay, yeah, I can hear my voice again.
There's still an echo from your end?
It's just, there's a return back. It's not even an echo.
The return back. Okay. How about now? Is there still a return back?
Hello?
Hello.
Yeah.
Is there still a return back?
Yes. Yes,
It's
yes.
not this connector. Okay. It's not really there.
I think I will have to give the talk this way.
Okay. Okay, I guess.
So
but-
are you connected
yeah,
in the
but-
laptop?
I am connected in the laptop, yes, and the room system that we have here. Yes.
I see. Can you mute yourself?
I can mute myself. Yes, just a second. Here. I'm going to mute myself now. Okay. You try speaking and see if it works.
Yeah. Hello? Hello? Yeah, I can hear myself.
You can still hear yourself? Okay. Okay. So then, yeah, that's interesting because the only source of audio from my end is the mic.
Hello?
Hello? Hello?
Yeah.
Hello? Yeah. Hello? Yeah. Hello? Yeah. Hello? Yeah. Hello? Yeah. Hello?
Hello? Yeah.
I have a question for you. Prof, is it possible for you to try rejoining and doing it again?
I will try rejoin. Yeah.
Yeah.
Thank you.
So there's a thing with one of the participants is hearing his voice over and over again. So over on Teams, that when they present or when they're talking, they can hear their own voice back. So is this something that causing from our end or?
Something's got to be music somewhere.
This is muted. There is no voice here.
On their end. So when they speak, they can get the feedback.
Yes, from they can hear themselves back. So like they're speaking and they hear their own voice back.
Yeah, you think I could suggest them to turn their volume down on their end.
Okay.
I don't know if they want to mute it, but they need to turn it down. It's probably so close and it's getting feedback.
Okay. Let's see. Okay.
Yeah, I would tell them that.
Yeah.
If they're so close, I would turn the volume down.
Yeah. I have asked them to rejoin and let's see how it goes. Yeah.
Yeah, I gotta bring that different in there. And you haven't used Teams video.
Hi, can you try now?
Hello, can you hear
Yes,
me?
is there a
I
still
can hear,
echo
yeah,
on your
no,
end?
no, no, I'm good. Thank you so
It's
much.
better now?
Yeah,
Okay,
yeah, thank you so
perfect,
much.
perfect,
Thank you.
perfect. Okay, okay then. No, I've just.
Oh, you got it
Yeah,
down.
yeah, okay. You should be able to.
Okay, we check what time to begin.
In any time now. So I'm just going to announce and then we start. Okay.
We make, see what's going on.
Yeah.
You see my screen?
Okay. No worries. So let me just make an announcement and then we can start.
Yeah.
Okay, sounds good. Thank you. Perfect. Okay. Hi, everyone. We have our next speaker, Professor Evangelos Theodorou from Georgia Tech. And in one of the earlier presentations by Professor Christos, we saw some of the demonstrations of the methods that was developed by Professor Theodorou's group, and he's going to tell us more about it in his presentation. The floor is all yours.
Yeah. Can you hear me?
Yes, we can hear you.
Okay. Yeah. So thank you for the kind presentation. And I'm really sorry I could not be there due to an obligation I had in Europe, which was a last moment conflict. Before I start, I would like to thank Naira for all of these years of leadership. First of all, putting the team together and keeping us with keeping up with all of us. I think she has demonstrated leadership. I don't think that we could have been able to work all together in this project without her work and patience. And then I want to also thank. I think Irene is there in the room. I want to thank her together with Michael, also from NASA, for all the meetings we had all of these years that kind of push us to think a little bit outside of our comfort zone, and for their support over all of these years of work within the ULI and outside of the ULI project. And so today there are 4 concepts that kind of highlight the work that we did for this project. And I think the first part is something that Christos Papachristou from University of Nevada, Reno, talk about regarding covariance steering control and trajectory optimization. I'm not going to spend a lot of time on this because I think Christos already talked about it. It's a covariance steering optimization methodology that we have developed. But then I'd like to spend a little bit more time on a few concepts that came out of the work in my lab during these 4 years, which is how do we essentially handle non-convexity in trajectory optimization methods, especially when they are used in planning systems for planning. Especially the domain of autonomy. For the domain of autonomy, planning is a non-convex optimization problem, right? There are always many ways to go to your target state. And then the last part of my talk is going to be more kind of open-ended. We have some really nice initial results on this technology, where I will be talking about deep unfolding and the ways how we can merge what people call artificial intelligence or what people call deep learning with traditional optimization methods to overcome some of the fundamental limitations that both of these tools have. And so starting from covariance steering, okay, so this was a method that we developed in our lab. The idea is that there are plenty of methodologies that can do covariance steering. The idea here was to split the optimization problem such that we can make the optimizer to be more forgiving during the first iterations of optimization. So basically allowing some constraint violation during the early stages of optimization, but then as you are approaching the optimum, you can essentially satisfy your constraints. And the way how we did that is by a method that is used in optimization, which is called operator splitting, which means for the context of covariance steering optimal control problems that you split the trajectory optimization for the mean of the stochastic system and the trajectory optimization for the covariance into 2 separate blocks. And then you try to achieve a consensus between these 2 blocks using an augmenting Lagrangian methodology. And so we did some work in simulation and in some terrestrial vehicles. And then, of course, there is a whole work that we did with Christos on the hardware. In general, the way how one lesson that we learned from that hardware experiment is that it's basically that it's okay. Let me go back. So this is the experiment. I think you have seen it, but I think one lesson that we learned, we had really limited computational capabilities on this vehicle, and we had to make approximations that will allow us to pull this demo forward. And I know that there was a question before about vision. So when it comes down to hardware, I think universities will be benefited quite a lot if in some ways this hardware is available to them, right? So as universities is, of course, Christos is an exception here. He's an exceptional researcher in building a hardware, but it's difficult to build a hardware knowing what are the demos that you want to be able to pull forward, right? So ideally, it would be great to have a GPU on this vehicle, right, and do all the things that we have done on terrestrial vehicles. But given the resources that we had, this is the demo that we were able to pull forward. So I just want to say that the bottleneck typically when we do research in universities is the availability of hardware and how many resources we have to pull off to be able to build this hardware. Okay, so now I'm going to go to things that kind of excite me a lot, and these are things that we did for this particular project. We have, in my lab, we have developed stochastic optimization algorithms, and the motivation was always to handle the full nonlinear dynamics, the full non-convexity and non-smoothness of the optimization problem. And some of these methodologies at this point are very mature. Here I'm just showing a video from a project that we were involved together with JPL on this off-road navigation platform, where we basically use stochastic optimization algorithms like, for example, MPPI, to be able to handle all the nonlinear dynamics